Thank you, Stuart. I'm going to present briefly what we are doing in Work Package 4 on mechanistic modeling. As Stuart mentioned, part of the aim of SusCoRD is to provide understanding to the phenomena that occurs that prevents corrosion when using organic coatings. And the reason why we're doing modeling and simulation is because we can test hypotheses, we can complement experiments, we can help interpret experiments, and hopefully we'll develop models that will be able to predict performance. The team behind the Work Package 4 is a large team. We have people in chemical engineering here in Manchester, in materials here in Manchester. We have researchers in Sheffield, and of course in AkzoNobel. I will let Simon present the relevance of modeling to AkzoNobel, and then I'll continue with the activities we're doing.
Great. Thank you very much, Flor. That was good. So all I was really going to say, I mean, the relevance is hopefully, come out of somewhat what I said earlier. Should be fairly self-evident. We have systems that are, coated across a wide range. I mean, we see a severe, environmental exposure in the top left. Wind turbines themselves are basically often in highly hostile environments. Buildings need to work at the bottom as well as at the top. Aeroplanes have this horrible habit of going up as well as coming down. Perhaps one of them, wherever, is the better one. So to do that, to be able to actually make systems that work, we have to understand performance. Now, performance on day 1, day 0 is relatively all right, but these systems have got to last for tens of years, and that requires us to understand not just how they're working on day 1, but what the degradation mechanisms are. So very much what we're interested with the modeling is to give us the way of basically testing our hypotheses. So being able to say, this is what we think is the method by which this coating is working. Can we look at long lifetimes? Can we look at tiny scales via modeling that we couldn't look at otherwise? And so we hope to get out, tools for prediction, and those in the end will give us shorter development times, will give us improved performance, but also importantly, they'll allow us to change the ingredients we're using, because we can do experiments, and that's going to be key when we think about new ingredients. Now, coatings and sustainability, this was called SusCoRD, and part of that is to enable a transition of the coating ingredients towards more sustainable ingredients where appropriate, but more importantly, that improved performance will give a huge sustainability benefit. That was all I was going to say, Flor, so back to you.
So from an academic point of view, why are we interested in modeling and simulation, and in particular for this project? Coatings are complex systems. You have heard this phrase more than once through this meeting, so I'm not going to elaborate more on that. But modeling and simulation can provide fundamental understanding and can help us to predict behavior. Fundamental understanding comes out of knowledge generation, and we want to better understand the properties and the behavior of the coating. For predicting behavior, we need to develop models that have been validated, that are robust enough to be able to predict behavior of materials. The challenges that we face is validation of the models that we develop. We have an hypothesis, we build a model. Is that model represented by reality? Is there data to validate those models? And sometimes that is quite a challenge, and it's good to be part of this project where some of this data is also being generated. Accuracy of the prediction. Are we predicting trends, or are we doing quantitative prediction? Something that is sometimes overseen is the time that it takes to develop these models. Can be significant. The time that it takes to run these models, to do the calculations or the computing power that is required, can be also significant. If you were here on Tuesday, you heard Simon's talk about the cellular automata, the advantages of having a simplified model to describe a system. that doesn't require significant calculation time or computing power, but that it also has some restrictions due to its simplicity. So it's always a balance between how detailed is the model and how much time and computing power is needed. Other challenges is once we have a model that describes a system, can we transfer it to other system? How reliable is going to be? And finally, each model will require some input parameters. Do we have those input parameters? Are they reliable? If we use input parameters that are not reliable, the results from the modeling may not be satisfactory. In particular, in this work package 4, we aim to provide robust and versatile models to describe the performance of cross-linked coatings with and without active inhibitors that can be used to understand physical and chemical mechanisms that lead to coatings failure, the dependency between the processes, and help identify key aspects in coatings that can be tailored to improve their efficiency. And we are going to look at phenomena that goes from the molecular scale, that is at the nanometer scale, to the pore scale, that is a micron scale, to the macroscopic systems that are at millimeters and centimeter scale. And we are going to use a range of tools from molecular simulation to modeling multi-component transport at the mesoscopic scale, and construct multi-physics models to capture the overall coating performance. We have divided the work package into a number of small projects and tasks. Some of you have heard about some of these during this meeting. And just to mention some of them, we are looking at the microstructure of the polymer coatings. Does it have porosity? Does it have channels? What is the structure at the molecular level of the coatings that allow transport of water, ions, and other species? What are the interactions between the polymer coating and the substrate, such as the energies of binding? What is the diffusion of small molecules through the coating? All of these are done at a molecular scale. You heard this morning, if you arrived early, the work that we are doing on leaching of inhibitors and characterization of the inhibitor connectivity paths. We are also working on, or going to be working on coating swelling and modeling macroscopic defects. The methods that we are using range significantly from molecular modeling, where each atom is represented explicitly, and we can calculate some properties, some macroscopic properties using molecular dynamics, for example, calculate diffusion coefficients that may be necessary for other types of simulation, like pore scale simulation or macroscopic simulation. In pore scale simulation, we have a finite element system where diffusion equations are solved. And in the macroscopic modeling, we are developing a multi-physics model to describe the effects of defects in corrosion. I'm going to let two of the researchers in the group give a short example of the work they have been doing. Charlie is going to talk about diffusion in coatings using molecular modeling, and Joe is going to talk about leaching of inhibitors using pore scale modeling. So Charlie, all yours.
Thanks for the introduction, Flo. So I think I showed this picture earlier in the week, but if we look at a bridge or something and the coating that's applied to it, it looks like this. So you have the structural metal underneath, which tends to form an oxide layer above it from pre-treatment. A primer is then applied, possibly some interlayers, and then a top coat. So as Flo said, I do atomistic simulation. So this is still far too big for me to look at in one piece. So what we need to do is think about what question do we actually want to answer at molecular level. And again, as Flo introduced, we want to look at the diffusion of water through these coatings, because if we for corrosion to actually occur on the structural metal or the oxide layer, the water needs to move through the coatings. And as Simon and Stuart said, we know that this happens. This is never going to not be there. So that's what I'm looking at. How do water and ions reach the surface, which is needed for corrosion? So to do this, I create realistic cross-link structures with different concentrations of water and ions in, and measure the diffusion and hopefully work out the mechanism for that behind it. So the actual system I'm working on today is a Gibbon epoxy with an MXCA cross-linking. And the really nice thing about SusCoRD is working with experimentalists. So this choice was informed by one of the researchers in work package 2. So hopefully we should play. Here's a video of one of my simulations. So I picked a water molecule at random in green, and you can see that it sort of spends lots of time in one region bobbling around in a free volume, then it will quickly shuttle through to another region that's got quite a bit of space, spend some time there, and so on, and that's how it makes its way through the coating. The nice thing about doing these simulations is that we have a highly precise control of different independent variables, and it's very easy to change them and keep the others the same. So things I've looked at are what happens with the temperature, what happens with the cross-link density, and what happens with the composition. So this could be what you've actually got in there, so what cross-link you've got, what amine you've got. But today when I say composition, I mean the amount of water present. So I've looked at from 0%, so completely dry films, all the way up to 5% weight water. And from these systems, what we can actually look at is we can get a video, which is very nice but not very quantitative. And we can look at the water and polymer mobility and actually get out some numbers for the diffusion coefficients of water through these systems. We can look at the structure, so what pores are there, what free volume is there inside it, and we can look at interactions. So where is the water? Do we see microphase separation and clusters of water, or where does the water like to sit, and are any hydrogen bonds formed? So if we do that, we get out the diffusion coefficient versus the temperature for different amounts of crosslinks. So what we can see is with temperature, for all crosslinks, the diffusion coefficient increases, which makes sense. There's more kinetic energy, everything moves faster, your water diffuses faster. What else we see is that as you change the amount of crosslink, the water diffusion decreases at all temperatures. So this is as you're starting to form crosslinks, the water slows down. What we see, which surprised me slightly, was the water diffusion rate is basically independent of the water percentages I looked at. So for all the systems I looked at, this was sort of the limit, didn't really have much effect. The nice thing about doing simulations is we can go in and look at it. So this is what, under a very powerful microscope, my coating would look like. So you can just about make out the atoms shown in this sort of transparent colour. And these blue regions, these are the surfaces of the voids. So inside these blue regions is where the water will sit. It's where the free volume and the empty space is. So for all the systems I looked at, all the temperatures, cross-linking amounts, water percentages, they had this system of isolated pores. And what I was able to do is characterize these pores and look at the proportion of large pores. So when I say large pores, you'll all say they're tiny pores because they're still on the nanometer scale. So large pores, I mean they're large enough to fit a single or two water molecules in. None of these great big micron-sized pores. But you can see that the trend in large pore sizes is very different from the trend in water diffusion. So that's probably not the main cause of the water diffusion trends. If, however, we look at the polymer mobility, so again, this is a diffusion coefficient, now it's versus cross-linking amount with different temperatures, you can see that for, say, 450 Kelvin, you get a 2 orders of magnitude change in the polymer mobility as you cross-link these systems. And if we compare the trends here, you can see we get the same trend in polymer mobility as water diffusion. So that suggests that it's actually the flexibility in the polymer mobility of the coating that's the key factor in controlling the water diffusion rate. So basically, we've got an improved understanding and identified a mechanism for water transport through these cross-linked polymer coatings. The water spends time in these isolated voids. The polymer then moves and lets the water out. It hops to a new void and so on through the coating. And this has impact on the cure time, so this is related to the cross-link density. And if perhaps you over-cure your system, or you under-cure it, or you haven't mixed it properly, or your composition is slightly off. And also the environmental effects, so the temperature and the moisture content. So the next steps for this is to move on to ions, which are equally as important, if not more important, with corrosion, but are slightly more difficult to model. So with that, I think I'll pass over to Joe.
Okay, so I'm just going to start with a little bit of background and kind of my little bit of the project. Just to start with, again, the cost of corrosion in the UK, £65 billion per year, contributes over £11 billion to the economy and supports manufacturing worth more than £150 billion. So this is really an area we can have a huge impact on if we can improve our anti-corrosive coatings. So for us, we're using looking at organic coatings applied to metal to stop corrosion, and they have many applications from consumer packaging to the aerospace sector. However, coating failure / damage can then lead to corrosion. So these active correction protection coatings are a polymer matrix loaded with corrosion inhibitor particles. Here's my little schematic. You've got little bits of filler particles in there as well. And these corrosion inhibitors will dissolve and diffuse, forming a pore network in the coatings. This is then, if the coating gets damaged and water gets in this area, the inhibitor particles can then dissolve, and then the next one dissolves, and this forms this pore network. And then those corrosion inhibitors react with the metal surface to form a protective layer. So here we can see an image of a real coating, with all the different colours kind of showing the different inhibitors and fillers inside there. So our aim is to model this process to get an understanding of the underlying factors which affect the dissolution and diffusion. And so by doing so, we're going to create models for pore formation, leaching, and the formation of the protective layer, with the aim to develop better formulation decisions for manufacturing these coatings. So today I'm just going to talk about the dissolution and diffusion of the coatings and the formation of this pore network. So our nice simple starting model. So for this, we've had to develop a numerical model, which is a time-stepping moving mesh algorithm. And if we just let this go, so we start with water on the right-hand side and the boundary of the inhibitor on the left, and then it starts to dissolve and diffuse, so we can see the colour as it kind of comes out. And we can look at how much mass of inhibitor ends up out in the water with time. So we don't expect these inhibitor particles to exist in isolation, so we expect we're going to have more kind of touching in different directions, and this means we now have to split our boundary, and then we may need to rejoin our boundary if there's another inhibitor particle. But we don't expect there just to be one particle touching where the crack is and where the water's got in, so we may have more, and that may be connected to more particles and more particles, and then there'll be some particles that aren't connected to our other particles, so that when we solve for this, our method is able to start in multiple places, it's able to split and move in multiple directions to dissolve the different particles, and then reform and join back together, as we've just seen here. And again, the whole time we can track the amount of mass that's coming out into our water. And here I'm using circles just for convenience, but we can look at particles of any shape or size in any distribution to then investigate how those different shapes, sizes, distributions affect our dissolution rate and how much mass we end up getting out into the water. So finally, I've started investigating what's called a Gaussian pore space. So this is a method of creating a random network so that we can characterize these in terms of pore network characteristics, such as volume fraction and tortuosity, then compare that to kind of how well or how quickly the salt dissolves and diffuses out into the water, and then relate these pore network characteristics to manufacturing parameters such as particle size and distribution, so that if we do a lot of these simulations for a lot of different random pore networks, we can get statistical data on how, just by looking at it, we already be able to know how well this is going to work, so that when we're kind of looking at manufacturing these, you can put one together and say, oh, well, I've got a certain particle size or certain distribution, and we should already know or have an idea of how well that will work. And back over to Flo.
Sorry, I missed the last slide. That's fine.
Sorry, on last slide. So it says quick summary. So that's my mathematical. I've created a mathematical model of inhibitor dissolution and diffusive transport. created this numerical model, which is a front-tracking moving mesh algorithm, and started identifying pore characteristics, limiting dissolution, and how they affect the leaching process. My next steps are to characterize these meshes for random pore networks and link them to manufacturing parameters, and simulate over these meshes to generate statistical data. And finally, the impact of this is that we've made a real key step to creating a numerical tool for the rational design of new products. So thank you. Now I'll hand over to Flo.
Thank you. So, we managed to run just a little bit over time, not too much, but I just want to wrap up the presentation of work package 4, saying that we are collaborating with other work packages looking at binding energies, polymer properties, diffusion in polymer, leaching from polymers, and we're going to start looking into problems of diffusion and segregation at the polymer surface interface. Some interesting things that we can do is look at a comparison between the cellular automata and the diffusion model and move to more realistic 3D structures. And the impact that this work package expects to have is to improve the understanding of fundamental phenomena to better enable coatings formulations. Thank you for your attention.